The stream multiplexer is a stateless abstraction layer responsible for combining multiple independent input channels into a single ordered output stream. The multiplexing operation preserves source attribution, metadata, while applying deterministic scheduling to interleave data frames. All operations are thread-safe through read-write lock acquisition at the channel registry level. Channel registration occurs at initialization and persists for the lifetime of the multiplexer instance. Channel priority assignment uses a numeric scale from 0 to 127. 0 represents the lowest priority level and receives processing only when all higher priority channels have been drained. Priority values are immutable after channel registration and cannot be modified through the public API. Channels with identical priority values are processed in registration order, which is stable across process restarts. The scheduling algorithm executes in a round-robin fashion within each priority tier. One frame is drawn from the highest priority non-empty channel, then processing moves to the next lower tier. Once the lowest tier is processed, iteration returns to the highest tier. This guarantees fair allocation within priority groups, while maintaining strict ordering across priority boundaries. Channel frame capacity is defined at registration and establishes the maximum buffer frames per channel before backpressure is applied. Default capacity is 2,506 frames. When a channel reaches capacity, further write operations return an error code indicating the buffer state rather than blocking the caller. This non-blocking behavior prevents deadlock scenarios in complex topologies. Frame metadata includes a source channel identifier, a timestamp in nanoseconds since epoch, and a sequence number local to that channel. Sequence numbers begin at 0 and increment by 1 for each new frame. Timestamps are recorded at frame submission time by the calling thread and represent wall clock time, not monotonic time. All metadata is read only after frame construction. The multiplexer maintains an internal state machine with 5 distinct states: initialized, running, paused, draining, and terminated. State transitions occur in a defined sequence. Running to pause transitions are allowed. Pause to running transitions are allowed. Only draining transitions to terminated are irreversible. All state transitions acquire an exclusive lock on the state register. When the multiplexer enters paused state, no new frames are dequeued from any channel. Frames already committed to output buffers continue processing. Incoming write operations to paused channels return successfully and the frames are buffered locally. This allows back pressure accumulation without data loss. Pause duration has no upper bound and may persist indefinitely. The drain operation initiates a controlled shutdown sequence. During draining, no new channels may register and existing channels accept no new frames. The multiplexer continues processing buffered frames in priority order until all channels are empty. Drain completion triggers automatic transition to terminated state. Terminated instances cannot resume operation. Output buffer sizing is configured at initialization and defaults to 8,000 frames. Frames are copied into the output buffer rather than referenced by pointer. This isolation prevents external modification of frame contents during processing. Output buffer overflow is not possible in normal operation because backpressure prevents overloading. Overflow protection is enforced at the frame construction stage. Frame filtering is optionally applied per channel through a predicate function reference. The predicate is invoked by the multiplexer immediately before frame dequeue. If the predicate returns false, the frame is discarded and the next frame in sequence is evaluated. Predicate execution must complete in bounded time. Predicates must not perform I/O operations. Metrics collection is available through a read-only statistics structure updated incrementally. Statistics include total frames dequeued per channel, total frames filtered, current buffer occupancy for each channel, and processing latency percentiles. Percentile calculations use a fixed-size histogram with 64 buckets spanning logarithmic time ranges. Statistics are point-in-time snapshots. The multiplexer implements adaptive load balancing through dynamic priority adjustment. If a channel consistently remains at capacity, its priority value may be decremented by the scheduling algorithm to prevent starvation of lower priority channels. Adjustment occurs once per scheduling cycle and changes are bounded to single-unit decrements. Adjustments are temporary and revert when capacity pressure reduces. Error handling uses a return code enumeration rather than exceptions. Codes include success, channel full, invalid state, invalid handle, and resource exhaustion. Each code corresponds to a unique unsigned integer value. Callers must check return codes after each operation. The multiplexer maintains no internal exception state and does not propagate errors through subsequent calls. Memory allocation occurs exclusively during initialization and channel registration. No dynamic allocation happens during frame processing or deque operations. All allocated structures use pre-sized arrays and fixed capacity queues. This deterministic memory pattern allows deployment in environments with stringent allocation constraints. Memory is released immediately upon multiplexer termination. Persistence of multiplexer state is not supported. The multiplexer is designed as an in-memory, session-scoped component. Configuration parameters may be written to durable storage and used to recreate an equivalent instance, but in-flight frame state is volatile. Serialization of frame contents is the responsibility of the application layer. Testing of multiplexer behavior requires creation of test channels with known input sequences and deterministic priority settings. Unit tests should verify scheduling order, priority isolation, backpressure handling, and state transition logic independently. Integration tests should exercise multi-channel scenarios with varying frame rates. Performance tests measure deque throughput and latency percentiles under sustained load.